Okay, hello everyone. We are in the middle of a season of design reviews for version 14, and I think today we actually have 3 design reviews, and this is our first one about numerics. So, PDs. All right, so Oliver.
Yep.
Are there new, are there new functions here, or this
Yep,
is,
there are. So solid mechanics is just extension of the existing framework, and fluid mechanics, electromagnetics, and quantum mechanics are new functions.
so there's we've got a finite element, and we've got this page, but that's not what we're talking about here.
No, that's correct. That's just for you.
Where's the guide page that shows new functions?
So there is a guide. I mean, there's a guide page for electromagnetics.
Okay, where is it?
So we have an overall guide page, and then there's one for each domain, basically.
Okay, all right, okay.
Yeah.
All right. Solid mechanics. All right. So you're saying I should pull this up?
You could if you want to. So solid mechanics doesn't have any new functionality per se. It's got extended, not a new design per se. It's got new functions or new models added.
That's a reference page, Stephen.
Yeah.
They're not a guide page.
Ah. Well, where is the guide page?
We don't point to it here. But if you go, that thing exists. If you just open that page, you can click yourself to the guide page.
Okay. Well, I mean,
or if you want to open the source for that solid mechanics page, you need to go to the ref page in Docker Tools.
I don't particularly. I'm just trying to understand. Okay.
So what's happened here is this very refined, submodels for hyperelastic solid, mechanics, basically. So not typically metals or anything like that, but it's like for skin and plastics,
rubber, foams, and stuff like that.
Composite material.
Yeah, composite materials.
What the hell is that doing there? That should not be in documentation. Ever. Why is it there?
What exactly shouldn't be there?
The thing I just highlighted, $history length equals 0.
Why shouldn't it be there?
Has nothing to do with
this is a monograph. It's not a guide page.
I understand that,
and it's not a reference page.
Nothing to do with why are you? You got to explain why you're doing that. What does that have to do with finite elements?
Okay, so it has
nothing to do with it.
Okay, I'll add a sentence to explain this in more detail. The reason it's there is that history length tends to take up so much memory that the finite element models potentially wouldn't run. So I'll add a specific sentence.
Why don't we handle that in a different way?
If I'd be happy to hear a suggestion how to handle that.
Well, you should bring it up. I mean, look, if this is a systematic problem,
I didn't realize this is an issue. So why would I bring it up?
We shouldn't be doing hacking like this.
It's not hacking. It's a system function, $history length.
I'm well aware.
Yeah.
But we shouldn't be, in 2023, we shouldn't be having to set that to 0.
Okay.
That was a thing that we invented in 1988.
No problem, Stephen. I'll get it fixed.
2 megabytes of memory. Why do we really need to do that? Because there's so much stored.
Yes. These models can potentially take gigabytes of memory.
Okay. And we're storing them. Okay, but we don't want to set history length to 0.
Okay, I'll fix it.
Many other parts of the system rely on that not being 0. And people will be very confused. But so what is the correct solution? What is the correct solution? I mean, do you need to keep around the versions of the models or not?
No, I don't need that.
Okay, so why then is it, okay, how do we avoid that then? If it doesn't matter, then we should have something where the thing that is the output, that is the giant model, like let me give an example. Okay, so for instance, okay, if I were to do, range of 1 million. Okay, it's going to grind away. And notice that it says store full expression in notebook, right?
Yeah.
Now this thing, probably this thing is still in memory, but it certainly
Yeah.
isn't in the notebook.
Yeah.
And my question would be, go ahead.
It's the memory that he's worried about, not the notebook.
I'm well aware. But my question is, when do you want to preserve it? When don't you want to preserve it?
I would never want to preserve it. Everything I want to preserve is stored in a variable. I never want to preserve anything
How do you
else
know it's stored in a variable?
because I assign it to a variable.
Okay.
Everything that I need is assigned to a variable. Otherwise,
Well, I
it's
think
not
it's an
relevant.
interesting systems level thing that we could
Okay.
have something that says basically don't assign the out labels if they're
Okay.
too big.
Yeah.
You see
Good.
what I'm saying?
Yes,
And
absolutely.
I mean, for your thing, I mean, it's something that just hasn't come up in 30 something years, this issue of,
Oh, it does come
looking-
up. I mean, you must see tech support interaction where this is still coming
Yeah.
up, you know, from tech support regularly.
All right, okay, well
But
then
of
we
course,
need a
if you
different
set
solution. Then we
if
need
you
a
set it in a
solution.
notebook, if you set it
Okay.
in a notebook, it's going to affect the rest of the session as well, and people may get confused about that. So we need something else for that.
No, it's a bad idea. That's why I said it's a bad idea, right?
Yeah, I
But
agree.
let's
I
think
agree.
about it. Yeah,
Okay,
right.
so I suggest I got the point. I'll take care of it. Let's move on.
No, I understand that particular issue. I just want to think this through for one more minute. I
Okay.
mean, basically the point is, and we should bring this up probably in the LCC meeting series, something which is essentially a setting that says if if the thing is too big in the pure outline, don't assign it to that outline. Don't kill history in the whole session, but just don't assign this particular out.
But that still has a problem because you still keep lots of stuff that's not larger than the quantity that you define in the if statement. I don't want any output. I don't want to store anything.
I'm sorry, you do want to store something. You want to store the thing that you set to a variable.
Exactly. That's
Right.
all I
The
want.
only thing that right, but the thing that is the problem is the stuff that has been bound to out 17 or something, because that is why it isn't
Right.
removed.
Correct. Yeah.
The only thing is the hook that is binding it to these out numbers, right?
Yeah.
And if you don't care about storing those,
Yes.
then that's the thing to do is when it is too big to store, when you want to save memory by not assigning the out number rather than blowing up the whole history.
Yeah.
Right?
Okay.
So that's the place to attack it. And I think it's a perfectly good idea. I'm sort of surprised I haven't heard it in 3 decades, but I understand your point.
Okay, good.
I mean, okay, now let me look at some actual content here.
So what you're seeing here is a collection of hyperelastic material models that are described with their accompanying theory.
Okay, so I mean, in this case here, let me just understand this. I would have thought the design of this would more look like the model name and then an association hanging off the model name somehow that gave the parameters of the model. What you have here is something where you have a model and then parameters, but those keys will be different for different models. Is that not true?
In some models. So a Lamé parameter and shear modulus is something you could very well specify for a different material model as well.
Everything. Those work for almost everything.
Yes.
But if you have some weird extra, laminar
right,
something
then they are also in a flat list. But if you prefer a deeper list nesting,
I don't know. I mean, I'm just raising that as a point.
For me, so one advantage of so it's probably both models would work fine.
Well, I think that insofar as something is shareable between different material model categories, it's better to have them in this flat list.
Yeah, I agree.
I don't understand this. This seems hackery. I mean, again, whenever there's hackery, we need to be, trying to figure out how to avoid whatever. Okay, let's take a look at this. So, I mean, It's
I mean, we could spend a lot of time on this, Stephen. It's
what is all this
it's
stuff?
That explains how to add your own
I don't
material
know.
model. So because these hyperelastic models are very different for different applications, people usually want to make their own models for a specific
I
situation.
understand, but I'm complaining about this kind of stuff here. That weird, you know, why does it need to be some weird thing like this? Why is this not just some generic, you know, thing?
you're looking at the lower level programmatic sort of interfaces as opposed to the more sort of ready to use.
No, I
This is
understand.
for advanced.
So
There's a whole
I mean,
FEM
so the thing
programming.
is, the thing with these, why they're in a PDE models context is very simple, that we are still developing the PDE model framework. And before I expose too many functions to system level or to whatever context, let's rather, especially for these super specialized functions, let's rather keep them in the context.
Okay, fine. Well, whatever. Why is there a print statement? I mean, print statements again went the way of the dodo decades ago.
Yes, so this is basically it's like a hello world program for material models. And for decades ago, we used to have a print hello world as a statement of a first program that you've written. And this is the first program you could write for a hyperelastic material model. So it's a homage to the old days of programming.
I mean, and this is a bad way to do this. I mean, we should be using lookup now. If data is an association, which I assume that it is.
Yeah.
You should use lookup. It's more robust than this.
Okay.
It does the right thing when it isn't there and so on. I'm just such a terrible person to give these demos to. I'm sorry. I mean, yeah, it's complicated stuff. I recognize this. I mean, I don't quite understand what, you know, it would be helpful to me, but it might not be helpful to anybody who's a specialist in this stuff. What is all this stuff?
So we had one customer, they wanted to model the hyperelastic extension of seedlings under the temperature change with global warming. And for those, they need hyperelastic models which have thermal expansion capabilities. So that's the type of things people do with this.
Great.
Yeah.
But to me, it would be helpful to have a sort of a map of all these various different funky models. I mean, again, I'm not sure it would help specialists, but just to give some sense of what, you know, the traditional Young's modulus, you know, then a little bit of Lamé parameters, and then you go very wild with all these kinds of equivalents of, you know.
I mean, in a way, the hyperelastic material model is part 2 of the structural or solid mechanics stuff. So there is a solid mechanics monograph that explains the basics, the linear type of the theory for it. So this is already, you're already looking at pretty advanced stuff, I'd say.
You've already gone wild.
Yeah, okay. we are in the wild area now.
Why is there an introduction that's way in the middle of the whole thing?
That's probably a mistake.
Seems like a bug. There's a lot of work, obviously, in all of this.
And maybe to just add something is, so the last thing you've seen down there is we've now actually also added capabilities a little further down, capabilities to add fibers to the material. So if you have like a concrete that's reinforced with steel, we can model this type of stuff now. So if you have fibers embedded into a material matrix, that's quite sophisticated already.
Even pre-stressed stuff.
You could even pre-stress it, yes. So if you want to build a concrete bridge that's pre-stressed, you could do it.
That's cool. I mean, so just to give me some sense, I mean, how close to the end are we here, so to speak? I mean, in other words, do we have at this point, you know, if I looked at the textbooks and so on.
Yeah. So there's two parts to this. So from the theory point of view, I think we've covered quite a bit. The last thing that we're now finishing off is the hyperelastic, the thermal hyperelastic type of stuff. And that's probably as far as I'd take it for now. From a Mathematica or Wolfram language point of view, there is two things that we should do. So the one thing is to define these models, we need something that's called an energy density function. And that expression needs to be taken, you need to take the derivative with respect to a tensor of this thing. And that's something that's a bit complicated to do now in the Wolfram language. So that's the one thing we should improve on, because
we're doing that soon.
And that's on the agenda.
Yes.
So that's the one thing. And the other thing is, because when we solve these things with a finite element solver, we need to take another derivative of these expressions. They become huge and potentially very expensive to evaluate. One way to remedy that would be to use automatic differentiation. So that's the two things in that direction for hyperelasticity. The other thing, so that's
it will be good to. I mean, we need a better framework in general for automatic differentiation.
Yes.
Probably yes. Yeah.
And I don't know how programmatic these things get. Do they have more than if statements? I mean, what level of
so the complicated thing is not so much the if statements. It's finding the derivatives of these energy density functions. That is really complicated.
But these are not algebraic functions. These are some kind of programmatic.
No, they are. But they have matrix variables. And so you have to differentiate with respect to those matrix variables.
Right.
So you get then like a derivative of an inverse and stuff like that. So
it is something beyond algebraic. So the derivative of a matrix inverse, for example.
Yeah. That's what I need to pursue this further, basically.
We're doing that in the calculus and algebra team.
Yeah. So that's something that's happening.
All of these things are differentiable.
Yeah.
Like that trace of c squared and
yes, stuff like that needs to be
all of that's all differentiable.
Yeah.
I have no idea what the correspondence is between these kinds of things and corresponding features of space-time. I don't know whether probably a lot of these exist there. I don't know whether.
Yeah, but it's not. I mean, so the people that need sort of being able to differentiate with respect to vectors and matrices and potentially higher rank arrays, it's like in machine learning, it's in statistics, in optimization, and this areas like this, signal processing, control theory. A lot of areas are using basically matrix calculus.
All
right. So anything else I should particularly look at here?
No, I think that's good for now. Yeah, it's everywhere, Stephen. I got the point.
Terrible.
So one thing why this is cool in the Wolfram language is if you want to use these models, you either need the material or the model parameters from either a paper, but typically you'll get them from experimental data. And doing the fit and then using this data in the model is super easy in the Wolfram language. I think that's a huge plus compared to other commercial finite element solvers. Because I mean, it's like find fit is so trivial, and you can directly use the result from find fit in the model. I think that's pretty good.
By the way, another picky point.
Yeah, go ahead.
I just magnified this thing, and the formulas didn't magnify. That's bad.
Yeah. Is someone PMing this? Maybe that, because that's certainly a thing for the front end.
Maybe I will share that.
Okay, thank you.
Yes.
Yeah, it would be nice if it was possible this is such a common thing, slash dot, whatever. I don't know. I mean, something we maybe should have a discussion at some point about whether we can modernize that approach. Using something more like lookup here. Apply solution or something, or apply. All right, let's go on.
Yeah.
I mean, I'd love to learn more about solid mechanics, but I don't think this is probably.
It takes. I mean, I don't understand all that. 2 years ago when we started, I knew I really didn't understand it, and then gradually we spent more time on it. But it's like you have to really dig in. Actually,
yeah.
This is. I think it's probably the most complicated PDE modeling that I've done so far. Solid hyperelastic material models is complicated.
Right. But I mean, in a sense, it's kind of like, well, okay. I mean, we've got stress and strain. I mean, in the end, are you computing stress and strain?
Yes.
Or are you computing, but it's just very complicated to do that. And the relationship between stress and strain is complicated and so on. Is that right?
Yeah, the models are complicated. And there are modern approaches that try to simplify this. Because, I mean, keeping track of all these different forms of stresses and strains is just a nightmare.
But I'm just trying to understand. The bottom line is you've got a stress and you want to compute a strain. Is that right? Is that
the other way around? So you've got a energy density basically, and from that you want to compute the deformation, and from the deformation you compute the strain and then the stress.
Wait a minute. I thought stress was the internal forces and strain was the deformation. Am I wrong?
So think about it. So stress and strain are related by the material properties,
Indeed.
so to speak.
Yep.
Yeah, good.
That's what I'm trying to understand. I'm trying to understand, in the end, if we wanted to have a master function that would work for every material, does it just say, essentially, strain tensor equals function of stress tensor, or is it something different?
It's strain tensor is function of deformation, and stress tensor is function of strain tensor and deformation.
Oh, so there's a separate. I thought the strain was the deformation, but what's the? Yeah,
it's related to the deformation. Yes. Yeah.
What's
so maybe if you want to, well, yeah, if we say that this is okay, then you could say it the way you propose. Yeah.
Okay, but so then what we've got is,
well, what we solve for all the time is displacement.
So
yes, I understand.
Yeah,
I understand. But in the end, the master function is, and it depends on position, et cetera, is, deformation / strain equals some function that depends on the material of stresses, but it's still assumed to be a local function. Is that true? That is, if you know the infinitesimal stress at a particular point, then you know the strain at that point. Is that true, or is that not true? Or is it more global?
I don't think I've seen a model where it's not local.
Okay. Even when you got weird pre-stressed concrete fibers and things in your.
Yeah. Well, those are basically then you just rotate the local components so that they work in a normal XYZ coordinate system.
Fine. But the end result is it is a local function. So it says strain tensor equals function of stress tensor for positions X, Y, Z.
Okay. Yeah.
So I don't understand why all of this stuff. I mean, if I look at one of these random models.
Yeah. So
where am I seeing the actual PDE?
Just scroll down somewhere further down. So you're looking for the W, capital W. That's the strain energy density function. There's one. So there is one. So Neo-Hooken. So C1, I1 minus 3. A little for, that's the strain
those
energy.
Things are in fact functions of X, Y, and Z. Is that not correct?
they're functions of the deformation gradient, and that is a function of the displacement, and that is a function of XYZ. Yes.
Okay.
Ultimately,
fine.
yes.
Right, but this, which is a bit confusing here, most of the time in the system, when something is a function, like in a PDE, we show that it as a function.
You'll see that if you evaluate this the solid mechanics PDE component. Then you'll get all the stuff resolved, and it's incredibly complicated.
Okay, I understand that, but I mean, where is a picture that? Sorry, where is it actually solving a PDE? I'm trying to look for that. To element mesh, it's got elements, but where does it say solve the frigging PDE?
Yeah, so we're looking. So there is a parametric undo solve.
Okay,
so
great,
that's where
okay,
the thing is generated.
I see. Okay. This doesn't look too bad.
I think this is
good,
it's pretty good, I think.
Yeah, I think it's quite good too.
Because, I mean, expressing something complicated like this, I mean, basically, it's just the two lines there. You have the material, neo-Hookean isotropic,
right,
and the fitted material data. And
yeah,
that's it.
Pretty reasonable. Right. I mean, and what's inside here?
I want to get more slack out of this.
Yeah, okay. It's impressive.
Good,
okay.
Thank you.
It really is. So this here, where was fit neo-Hookean? Somewhere up here. All right, so this is all preparation of.
This is making a different model. So this is a Gantt model. It's a different type of model. So in this notebook you're looking at, we're comparing all hyperelastic material models we have. We generate some random or semi-random, or like we generate some input like experimental data, and we fit all models to that to show the differences and to show how this fitting process works.
Okay, I understand. So just to give a comparison, I mean, like for example, for I don't know, Phong shading, Garot shading, all these kinds of material properties with respect to light, we've sort of, that seems very similar to this in terms of its sort of.
Actually, so we did something much more detailed there, which is called PBR, or physically based rendering, and that goes like far beyond Garot and Phong and so on. But nevertheless, it's sort of this kind of approximation of components.
Okay, but so I'm asking the infrastructure that we have for physically based rendering versus the infrastructure we have for FEM. Is it similar? Is it not similar? Like if I'm going to describe
I don't think it's similar. So my understanding for the physical based rendering is, and that's my limited understanding, is even though it's called physical based rendering, they still try to mimic the appearance of materials. Here we are actually trying to really compute the exact solution, or I mean numerically exact.
I get it. Yeah. That's not the level that I'm asking it at. What I'm asking is, when we have, I don't know, some kind of shading material property for, something. I don't know. What's the function that we're using for that, Roger?
Material shading. Actually, the material shading is the main.
Okay.
But there is a monograph for it that sort of goes into detail to explain.
Okay, so here we've got things like, metallic coefficient, roughness coefficient, et cetera, et cetera, et cetera. So what I'm asking here is, as we get down into the details of those, gosh, I can't believe there's enough examples here. Cannot believe it. Okay. I'm just trying to understand, again, we've got these particular properties that we are calling out in some way here. And I'm just trying to understand what the analogy between that and what we're doing for, I understand that this is just make the right picture as opposed to compute the PDE. I got that point.
I mean, maybe solid mechanics is not the right PDE field, maybe things like electromagnetics would be more suitable, or quantum mechanics even, for how properties appear, how material appear and stuff like that, you know?
No, I'm not talking about that. I'm not talking about what comes out. I'm talking merely about the software bureaucracy of what's going on. Okay?
Mm-hmm.
We have a thing here called material shading, and it has an association with a bunch of properties.
Mm-hmm.
Okay? You have a thing called solid mechanics component.
PD component, yeah.
No, right. Okay. And it has a bunch of parameters here, which presumably are sort of like these parameters here, right?
Yes.
So I'm asking whether the bureaucracy of these things is similar. Do you get what I'm saying?
I think it is roughly. The goals are a little bit different.
The reason it matters that they're similar is, we're going to have various kinds of, we do have various kinds of management functions for dealing with these kinds of things. Mm-hmm. Whether it's, merging associations, whether it's the lookup function, whatever else. And, we want to be able to make those work as broadly as possible.
Yeah. I think generally speaking, for these specs now that we've gone to associations almost everywhere.
Yeah, I understand. But then, for example, the conventions that we have, I just take a look at it. Just make sure that there's a correspondence. It looks reasonably close, but we might as well just make sure it's actually the same. Okay, I better go on to fluid mechanics. We have Sandor on our live stream, who is a fluid dynamicist. Good. All right, let's take a look.
Okay, for this one, we have a first go at a laminar flow PD component. Right now, we don't have any boundary conditions for them. And the reason, no, that's the monograph. You don't want to look at that. So you'd have to look at the ref page for the laminar flow PD component.
Well, that's what I tried to pull up. I said get function page and didn't work.
Oh, really? Okay.
That's what I just did. Oh,
that looks better.
Yeah.
So the reason we don't have boundary conditions yet is because fluid flow, there's many different aspects of it, and I want to make sure that the boundary conditions fit all other types of flows that we have or that we want to have. And customers right now, they can use Dirichlet condition and Neumann value to specify the boundary conditions, and we'll fix that or improve on that when we have more knowledge about the area.
Okay, so I don't understand. I mean, there's dynamic viscosity, kinematic viscosity, bulk viscosity. There's many viscosities.
Mm-hmm.
Those three.
Yeah.
Which are all features of I don't know what this means. This is I see Newtonian or thixotropic fluid or whatever the heck else it is. Well, do we have Newtonian fluids working?
Yes. Newtonian and non-Newtonian fluids are implemented. So we have 4 or 5 models for non-Newtonian fluids, and there you see your sublist of parameters. So you have a model name, and then you specify the subparameters for the specific model.
I wonder if this is the right way to do this documentation-wise, or whether we should have sub-pages for all of this stuff. I think it would be clearer to have sub-pages with their own examples.
How would we link? I mean, how would you find the subpage?
You just have links to them, and we have. Just like we do for something like formats.
Okay. Yeah.
That would be a look. If it is a thing throughout the PDE area that we're dealing with material models, which does seem to be a thing. It seems like material models is a thing both in the PDE area and in the 3D graphics area and so on. And maybe we should simply have pages called material model pages. Roger, what do you think?
Possibly. Can we hold off maybe one more release and then decide that we switch into that when we know a little bit more?
I think it's going to make sense because I think it's just too much.
I suspect
stuff
you're right too. I think they get too deep, just
Mm-hmm.
too much.
And it's much nicer to be able to have, the carry you model.
Yeah.
But by the time you're looking for a carry you model, you're going to want to see 3 canonical examples there, right there, of that model.
Yes.
Okay.
I suspect you're right. I think it's what it looks to be.
Okay, so let's say I want to do something. I mean, flow around a cylinder or something.
Mm-hmm.
Well, you don't have boundary conditions, so we're out of that game. Is that correct?
No. You misunderstand. We have boundary conditions. We just don't have fluid flow specific names for them. So you have to use Dirichlet condition and Neumann value to specify the boundary. We can absolutely solve fluid flow around the cylinder.
So when we add boundary conditions for a domain, they just make it easier to do for the typical cases that come up in that domain.
So it's like no slip
Yeah,
boundary.
Exactly. Stuff like that. We haven't implemented that yet.
Okay.
But you can model this, and there's examples of that.
Sander is commenting. What is the component of a laminar flow? Laminar flow PD. Well, I don't know what is this thing? What is this? This is a piece of, I don't understand what this is.
The laminar flow.
Typically, you're going to set, the right-hand side to something like a Neumann value or something. So this is not an equation yet.
No, I understand that, but what is it?
So the laminar flow is a combination of a momentum equation and a continuation equation. So
continuity equation.
Yeah, continuity equation. Yeah. So we have the Navier-Stokes part and the continuity equation.
Okay,
there.
So here it is.
So it returns so in 2D, it returns 3 equations, and in 3D, it returns 4 equations.
Okay, so that component, I don't even know what variables it has in it. It's got, I don't understand. It's got a velocity field.
Mm-hmm.
It's got a pressure somewhere, probably.
Mm-hmm. Yeah.
With some external forcing function, perhaps.
Yeah.
Sandra's asking what the laminar piece means. It's certainly true that
so we can.
The Navier-Stokes equations are they're supposed to be valid when nobody really knows absolutely for sure, but they're supposed to be valid for turbulent flows as well.
And you can use them for turbulent flow, but we don't have models for those yet. So I wanted to call this laminar flow to say that this is really, it's not, you can't model turbulent flow with this. It's just not.
Well, I don't understand what you say, you can't model it. I mean, in principle, if I just solve the Navier-Stokes equations for a Newtonian fluid flowing around some random boundary, if I solve them correctly enough, I will get turbulent flow. Right? They are just
but you need to have a turbulence model for that.
No, you don't. No, you don't.
What you're talking about is the Kalman vertex street, and we can solve that. But that's still a laminar flow type of flow.
No. The equations of fluid dynamics, these equations, so far as one knows, in the current state of mathematical physics, it's still slightly unsolved, but so far as one knows, these equations, were one to solve them in a condition with a Reynolds number of 1,000,000, one would get turbulent flow.
Right, but we can't solve that.
No, I understand that, but we can't solve it, not because, in principle.
So I assume
computer.
I know, Stephen, but I think what Oliver is saying, those turbulence models break down and make it possible to solve for reasonably high Reynolds numbers.
I know. You can
with finite element technology. Sorry?
You can put in eddy viscosities and all kinds of things like this, which are empirical ways to approximate turbulence, the effects of turbulence. Sandra is commenting on our live stream in capital letters. There is nothing to model. There is no model needed. It's if we really want to get persnickety about it, we can ask the question, we can, I mean, the existence and uniqueness of solutions to the Navier-Stokes equations is still an unsolved problem, revealing the fact that it could be the case that in certain turbulent flows, we're actually seeing kind of the shadows of things happening at molecular scale. But obviously, there's a lot you can do before you ever get to that. And it really isn't a, I mean, Sander is quite correct that this has nothing to do with laminar flow. This equation, these are the equations of fluid dynamics. They are not the equations of laminar fluid dynamics. And
I guess you want to rename the function
to fluid flow PDE component.
Okay.
That's what it should be.
Good.
And the question of whether it has a, I mean, normally I think most empirical modeling of turbulence has things like eddy viscosities. In other words, it really is just like these equations, except that there is an additional viscosity term added, I believe. Maybe there are other empirical models.
So one approach is to do it with a different viscosity term, yes.
What's an example of another approach?
Well, if you have a large enough computer, you can use the equation directly.
Okay, but that's why
and you just need
that's why that word is wrong.
Okay, got it. Yeah, I'll remove it. My thinking was it will confuse people that they use this function and expect it to work for turbulent models.
What do you mean turbulent models?
For turbulence modeling, yeah. High Reynolds number models.
Okay, but wait a second. High Reynolds number solving of the Navier-Stokes equations, or high Reynolds number solving of an empirical model that isn't the Navier-Stokes equations, that has some
high Reynolds number of the Navier-Stokes equation.
And why won't it work? They don't have a big enough computer.
Either because they don't have a So this version is because they don't have a big enough computer, right?
Fine. Okay.
So it sets expectations that we can't meet. But I grant you, so it's okay to do this change, because then in a potential addition, so if we use, for example, Reynolds averaging Navier-Stokes equation, we could use the same flow component for a turbulent type of model, which is useful for high Reynolds numbers.
Yeah, I don't see that there's really a big difference between, the fact that you're messing around with non-Newtonian fluids and the fact that you're kind of, which is again, messing around with viscosities and messing around with other kinds of things. You're kind of, I think the thing that is not untypical is to think of turbulence kind of like a bulk fluid, like a bulk, it's not like, I mean, from a mathematical physics point of view, it's its own derivable thing. It's okay. Let me give you an analogy. Okay, let's take heat. You could say, heat is something that one can successfully model as a bulk thing, even though it has dynamics underneath. And similarly, one can imagine, modeling turbulence in the same type of way as a bulk thing, and that, I mean, just like the fact that you're hacking, something which is really little, I don't know, red blood cells or something that are weird shapes and that flow in a weird way, you kind of hack them by defining some effective viscosity and so on. Similarly, you're hacking the fact that there's really turbulence in the fluid, but you're describing it in some empirical way.
I'll make the change. It's not the end of the world.
Yeah, but I mean, so let's just look at what this is actually doing now. So. Okay, so this is defining some equations here.
Terms, not equations, yeah.
No, I understand. Sorry, I meant terms. Okay, and then where do I put them in?
That's further down in the applications. Maybe you can look at a stationary example first. So this is a lid-driven cavity benchmark type of problem.
Pretty cool.
Hmm.
Why do we need to give all of this stuff?
Yeah, so the problem is that the Navier-Stokes equation is kind of what's called a saddle point problem. And unfortunately, I don't know of any way to detect these type of problems automatically. The way that's done or dealt with in the finite element world is that you interpolate the fluid velocity on second order and the pressure in first order. That allows us to stabilize these equations. And that's our method to do this. I hate it. I can't think of a way to get rid of it for now. So
okay, but hold on. I mean, just the fact that you have to give this method here rather than just saying method arrow automatic, and it knows you're dealing with, you know, fluid equations and so on because it looks at the symbolic structure of the PDE, right?
Doesn't really know that. I
Well,
mean,
then maybe we've resolved too much at that point. Maybe we should keep some.
I mean,
information
what is conceivable is that we have a larger a PDE model container, let's call it for a second, that has additional information like options that would be useful for the solver to find the solution.
I think that would be a good idea because I think what
Okay.
you've done here is you've resolved the PDE into raw equations,
Yes,
which is
indeed.
nice for
Yeah.
interacting with the Dirichlet condition and so on. But it means that you've lost the information. I mean,
Yes.
probably, I mean, I can't imagine that it's a difficult piece of heuristics or machine learning to look at the equations that you've been given and say, oh, that looks like fluid equations. I cannot believe that's difficult to reverse engineer that. See what I'm saying?
Yeah, I see what you're saying, but I couldn't figure it out. So maybe someone else smarter than me can do that.
But figure out what? I mean,
how to do that? How to analyze the equation and figure out that this is a fluid flow problem.
Okay. Well, I mean, you're looking for a truly algorithmic way to do that.
Ideally, but I mean, I'm open to other suggestions, of course.
Sandra is, by the way, commenting that she'd use the word steady rather than stationary. This flow is arguably not stationary. It's steady.
So I think what Sandra is
unsteady
commenting
flow.
about is, so you typically use the term stationary and transient for time independent and time dependent problems.
I think steady and unsteady is what's usually used, I think, in fluid mechanics.
Well,
sounds to me like you should send Sandra a draft of this stuff.
Okay.
But I want to come back to this because I feel like, Roger, I mean, you know.
Well, I think that you had it. I mean, I kind of believe Oliver when it says you can't tell from the equations whether it is this type of problem or not.
Well, except you can heuristically tell for sure.
Yeah. But I was thinking about sort of this thing of why we want to resolve it to equations so quickly.
Yeah.
And maybe that should be, I hate to do another object, but maybe that should be opt-in to resolve it, sort of an expansion when you want that.
Yeah.
I mean, if we had this PD model container, something like that, it would make my life a lot easier parsing these equations. So
then look at it. I mean, we have these kinds of issues also with regions and all this kind of thing. We can resolve them into raw, implicit equations and so on, but we often don't do that. Look, another point that's really simple here is when you say method, arrow, whatever, surely you should have a default fluid mechanics method where you just say method, arrow.
That's a good idea. Yeah.
Well, that's a really good idea.
That's a good idea. Yeah.
That would for sure.
That would already be quite. Well, That's a good idea.
We can implement that now.
Yeah.
Right now.
Right. Okay. Let's take a look at the electromagnetic stuff and the quantum mechanics stuff a little bit. Where do I go here? What should I look at?
Start with the electromagnetic PDE model. That's probably a good start.
This thing here.
Yeah.
Guide page.
Yeah.
If you use that other button, you don't have to use the Apple search, which is so bad.
Which button?
That one, yeah. And now,
Ta-da.
yeah, it's wonderful.
Oh yeah, that's much better. Just remind me about that every single time you see me
Yes.
get this wrong. Okay.
So again, electromagnetics is basically a phase one type of field of physics for us. So we've started with electrostatics.
What the heck is this doing with it?
Oh
That
no,
does
this
not
is
look like
this is
electrostatics.
definitely the wrong page. What? No,
No,
We just have the wrong picture.
that looks
Yes.
wrong.
Yeah. It's excluded. It's definitely wrong. But
Maybe you
Why?
intend to put a picture there, but that isn't it.
Yeah,
that's-
but the page generally is not
Well,
the right
that looks
page for
very
some
wrong
reason.
too.
Wasn't this one of the pages that that Stephen's computer had problems with? That over? Yes, this is not. No.
Okay, all right, okay.
This
fine.
is out of date.
All right. Well, we should try and track that down. But where can I see an example of some of this stuff?
Well, on the ref page, but you could look at the. Okay, open the.
You click the monograph.
Yeah, the monograph should be available at least in some raw format, in some initial format. Yeah. Try to directly go to the help page and help browser, whatever it's called, and look for electrostatics.
Really? The
Oh,
index
then you
has
get
been
the build
rebuilt?
version. Yes.
Yeah. So that at least then you can see something.
And you should have that documentation installed.
Yeah. There it is.
No, except it says can't be found.
What? Yeah,
Is
but
this
that's
useful?
not what we want to look at. No.
Is this an old one?
Yeah.
Well, maybe
Give me a second. Give me a second.
Yeah.
I'll,
you just
I'll
email it to me. Electric symmetry value. That seems very hokey to me. What are you going to give? Are you going to give the equipotential surface or something for the electrostatic? How does this?
just hold on a second. Oh, come on.
By the way, please take the O out of Schrödinger. That's not how we're doing it.
The O? You mean
No,
the
sorry,
E?
the E. The E.
Yeah.
I'm sorry, I meant the E.
Yeah. We can discuss this later.
We really should take the E out.
No. I
know your name has one
yes,
of those.
Stephen, what would you say if someone sent you an email where he spelled PH with F?
But with Scribner basis, we have a precedent that we have to follow.
I know we do, but Schrödinger, everybody in English writes Schrödinger without the E. Sorry,
Stephen, I'm German. You can't ask me to do that. It's just it hurts.
Yes, but I understand. Just think of how many non-British spellings we have. Like
Stephen, please, let's leave the E and
we cannot do it. We cannot do that. We can't do it. We're using American spelling.
Why would you use a wrong spelling?
Because let's use an Ö.
Yes, even better.
It is not used that way in English. It's like you could say what's a, I don't know, you could insist that the name of a city, I don't know, I'm sure there are names of cities that are translated from German to English. Right? So, how about Deutschland, right? There's a name that you certainly can't use, you wouldn't use in English.
Cologne. Yeah.
Totally unfortunately, Schrödinger, it's not going to work. It's not going to work. You can
use the accented character just with a O with
we're
a
not
thing
going,
on it.
it's not going to work. Look at 100,000 papers in English that use anyway, never mind. Okay, we'll cross that bridge later.
So I posted you a link in the chat, in the hope
Okay.
that you
Where
can.
should I go to that? Where should I go in the documentation?
Yeah, so if you paste that link from the chat into the documentation.
Okay.
Yes. Okay, now we have one. That's good.
Okay. So we've got some permittivity thing here.
Yep.
Oh boy. You know, engineers' versions of physics equations are just so horrifying.
Oh, that's what I think about physicist versions. Yes, I see the history links. I've seen it. We're gonna fix it.
Yeah, don't worry about it. Okay. So here's a question. Okay, so relative permittivity is relative to the permittivity of free space. Is that the idea? And so it doesn't have units?
Yes.
Per ISO definition.
Okay.
One thing maybe that I could comment on is that
this has a typo. This says permittive.
Yeah, that's a typo.
Yeah.
Yeah.
Go ahead. Units.
Is that in our material data we currently don't have values for electric electric material properties basically. Would be nice to have them in a future version maybe.
What don't we have? We have conductivity and things like that. What don't we have?
So if we have
permittivity and permeability, I'm sure we have.
If you look at like a metal and want to extract electromagnetic properties, there aren't any.
Like permeability, for example.
Yeah. Yeah.
Okay. Well, Michael might comment on that. I mean, I know we're redoing.
We are redoing the materials
properties, and we should surely have that. I mean, surely we can get that information. So that's an action item, I think, from Michael's team. Sounds highly reasonable to me.
Yep.
And is there an issue with? I mean, we're just using SI units, and that's all we're using. Right?
Yes.
So everything else is the past. Okay. That's beautiful. I mean, you know, your cylinder should surely be a bit taller.
Okay.
Not look so silly in all these pictures. I mean, it looks very squashed. That's a very minor point. Okay. So that's pretty cool. You can just say the gradient of the potential.
Yeah.
Get out the electric field. That's pretty cool. Now, what happens if I were using polar coordinates or something?
We have an axisymmetric version. So that is basically a truncated cylindrical coordinate system. That's what engineers typically use if they have rotational symmetry, but we don't have anything for polar stuff. And the reason is that the underlying PDE components like the inactive diff and inactive grad don't work with anything else than Cartesian coordinates.
Okay. Michael, does that bother you? I mean, I think it's going to be relevant in quantum mechanics, for example.
A little bit.
I mean, is it obvious how to do the change of coordinates if you need to, so to speak? I mean, in other words, if I have something in you know, that's represented in polar coordinates, can I reasonably easily, let's see, I'm just going to, these tables don't look as beautiful as they might.
Yeah, I'm not quite satisfied with that either. Maybe I'm going to center it again on the left.
Yeah, I mean, I think it also would do better with just the frame. It will look less floated.
Yeah.
It would be important to have the unit symbols not italic.
They're in math font.
But that's wrong.
Yeah.
But this is wrong. Units are per definition not math symbols.
Okay.
So that just needs to be solved. I don't know exactly how. One thing about this is, okay, let's say somebody wants to use this for a physics class. Okay.
Mm-hmm.
I suspect we should get somebody to rewrite this for physics classes to remove some of the things. Because if I go up and look at wherever it is, where did you have that table? Here, okay. Many of those parameters are unseen in a typical physics discussion, right? Like,
yeah, okay.
And we really want, I think, Michael, you can comment on this. I mean, it's just like, you know, D equals whatever it is, you know, epsilon times E or something, and no other sort of remnant polarization or anything like this.
That would be the only one you wouldn't see. The other ones, I think, are all fine.
Okay, fair enough. But I mean, even this equation here, right, is very fluffy compared to the physics version, I would say. Well, maybe it isn't in that particular case.
I think the only one that nobody would ever put the epsilon zero inside. The epsilon zero always is outside.
So, and maybe one thing to comment about is, so we have the additional challenge. So we want to solve this with a finite element solver. So we have to adhere to its underlying, well, needs. So it has to be in this form. And the cool thing about this is, and I think that's also interesting for physicists, is that you can actually transform all these equations, solid mechanics, fluid dynamics, whatnot. You can all transform them into this single one type of equations. I think that's pretty amazing. So I think actually it would be quite cool for physicists to I don't know, to take on a bit on that.
What is the type of equation?
So what you see, diff, blah, 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 grad, dependent variable, and then right-hand side and stuff like that. So it's basically the underlying, the finite element form of this single equation that we can solve.
Well, hold on. You're saying the outer thing on the is a divergence.
Yeah, on the braces.
Thing with gradients.
Yeah.
Is that right?
Yeah.
And the stuff that's in there in front of the gradient can be a tensor or a matrix.
Yeah. And that already describes to you what the boundary condition looks like. This is a really cool form.
I think the epsilon should stay in, but not the epsilon zero.
Okay, so I mean, are you saying it should stay? So here's the thing. For the finite element solver, I need the epsilon zero inside, basically. Yeah.
Why? You need the epsilon, but not the epsilon zero.
Yeah, the epsilon zero is a constant.
Yes, the epsilon zero is just a scale.
Okay, just listen. We don't have a finite element component that can solve A times diff grad. We just don't have that. So that's why I put the A inside the diff grad. It's not a problem.
You can divide by epsilon zero the whole thing.
No. You can't generally do that. If this is discontinuous, this function is epsilon r, whatever it is.
No, epsilon zero is a number.
But it just makes stuff complicated.
The argument Oliver is giving is that, I mean, I understand Oliver's argument. I think it looks a little weird here. But I'm trying to understand your statement that. So explain to me this.
Okay, open the Neumann value ref page, please.
Okay.
Everything comes from minimizing some energy functional. So, and starting from there is everything pure mechanics. Yeah. There's this big book by Tonti from a couple of years ago. Equations of physics has been written in this form.
So if you open
so hold on, Michael. What form? Tell me again.
I'll show you the form.
This form basically that Oliver has here.
Yeah. So if you open the details section,
yep.
So this what 1, 2, 3, 4, the fourth bullet point. 1, 2, 3, 4. Yeah, that has basically the first thing after the note dot is basically the type of equation we're pursuing.
Okay, but so Michael, can you explain to me why all these equations are of that form? Because there's an energy functional.
Because there's the energy functional, the quadratic in the momenta, and that's kind of it.
Here's a different explanation why all of these can be put into this form. Because basically this equation has all types of derivatives you can possibly have up to second order, and all combinations of it. So for up to second order, everything is covered with this equation because all type of
derivatives with respect to space and time.
Yes.
I think this is let's discuss. Correct. Because there are the ones of mixed hyperbolic elliptic type.
Why would
like
yes,
but they don't follow in this class.
What term doesn't follow into this class?
No, you cannot write them in this form.
Like the equations of transonic flow, for example.
This I don't know.
I mean, so the equations I'll restrict.
Oliver, you can
I'll restrict my statement. The equations for physics that we've dealt so far with could all be transformed into this form. So fluid dynamics, solid mechanics, heat transfer, mass transport, acoustics, all of this works in this single form. And
yes,
I think
but
that
not every second order PDE can be transformed into this.
I'll retract that statement. But for the fields of physics that I've just mentioned, we can do this.
Yeah.
Even though some of those fields of
physics is just an optimization problem, anyways, right? So maybe that's why.
With another small caveat that potentially periodic boundary conditions in infinite objects like crystals.
How do we find?
So this again should be a ref page.
In the source, Stephen. You have to use the source. It's not built. Because they're futurized, and it doesn't get built then.
You already had it open, yeah.
I would not call that the reaction term. I would call that the potential term.
I have commented exactly the same.
Michael commented exactly the same. So I made a compromise in adding this. The potential is modeled through a reaction term, but
I wouldn't call it a reaction term. Who calls it a reaction term?
I'll remove it. I'll give it to
if you're doing scattering theory, but you're not doing scattering theory because I can't imagine you have the boundary conditions.
I think the point is that people understand that even a Schrödinger equation can be modeled with a diffusion term and a reaction term. It's nothing else than that.
Yeah, I understand that, but it will confuse.
And I think it's an important point to make. There's only so few differential operators that you need to model a huge set of physics.
Yeah, that's interesting to you, but it's not interesting to the users of this.
Okay, I'll remove it.
There. Oh my gosh. Really? I thought it was called the orbital quantum number.
Ricardo, you want to comment on this? Azimuthal versus orbital quantum number. Have you seen?
I've seen both names used, so we could change that to orbital.
I don't know what's right there. I mean, my knowledge.
We'll do a web search and see what
45-year out of date. I mean, that's what I would have called it. That's what chemists would call it, I think. Michael, do you have a comment here?
I think both are fine.
We can add them both. So people can enter whatever they want.
Yeah. Orthotropic? What the heck is that?
Oh, it's an outdated page. Okay. So that means that the mass is different in the axial directions, in the X, Y, and Z direction.
When does that show up?
In effective treatment of solid states.
Yeah.
And we have, so we've changed that a bit. Yeah.
Yeah, you really need to get rid of these things because this really makes it look like we've just got the innards hanging out.
But this one depends on the X range. So this one you cannot so easily remove.
That's different, yes.
Look, what we're trying to achieve, guys,
I know,
is what we always try to achieve, which is you just need to know what you're trying to solve. You don't need to know the innards of the methods of the, finite element.
Stuff like that would be much easier if we had like a PD container, model container, or something like that, because then I know what I'm solving and I can adjust accordingly.
I understand that, but I think you can do, worst case is you could even do, machine learning based on the, the actual things you're given, because they're probably even the names of the variables tell you things. But
no, then it would be better to do it a few times and look how much the values change if you halve the max cell mesh.
Yeah, okay. All right. So this is in a potential. This is in what? I don't know what the potential is here.
That looks like a classic
the harmonic oscillator. So these should
be the X squared potential.
Which is a harmonic oscillator, isn't it?
Yeah.
So these should be Hermite polynomials.
Yes.
Times exponent minus X squared over 2.
Right.
Okay. That's cool. So if I want to get out the third one of these, I would literally just say
yeah, so these are lists now. So you'd probably use ND eigensystem with the third one, or just use ND eigensystem and take the third part of it.
Yeah, right. There's certain argument that parameter there should have a brace 3 version that just gives you the third eigenvalue.
Okay.
Does that make sense? I don't know.
Absolutely. I'm voting for this, Oliver, for this since years.
Oh, really?
Yeah, but especially for the chaotic conjectures for if I put 10,000 in. I wouldn't trust the 10,000 state.
Right. For those, we have the specific diffease solver that does this. Yeah, we can look at that.
Okay.
Eigensystem. So
don't forget to tell Devendra so we do the same for the symbolic version.
Okay. Yeah.
I mean, what about for eigenvalues itself? Do we have? We don't count eigenvalues. We just give all the eigenvalues for a matrix. We don't.
Actually, we can. No, we can give the top.
Oh yeah, we give the and yeah, right. We do that. So we should do the same thing there.
This is now probably a 14.1 thing.
Yeah, that's not something we.
Okay, so just so I understand, in let's say I was going to solve the Schrodinger equation in periodic potential, to get out Mathieu functions or whatever. And by the way, how much of this? Well, okay. How would I do that?
That would not work right now because you would need Bloch's theorem to get the Mathieu characteristics equivalent numerically.
Okay. So, I mean, this
you could solve with a certain boundary condition, but you couldn't get the full spectrum because, they form bands, so you have a dense, so you have a continuum, so it wouldn't work.
Right, so that's a mess. But in this case, this domain is infinite. I mean, in many of the cases, like with solid mechanics and so on, well, actually, I know I'm confused by that. In the case of solid mechanics, is it true that you're typically dealing with? No, I guess it isn't. Well, yes, it is a bounded domain. I mean, this thing, when you're sort of deforming that thing, it's certainly a bounded domain.
Absolutely.
But in the case of quantum mechanics, normally you're dealing with a nominally unbounded domain. I mean, like in that harmonic oscillator case, while the actual wave functions are localized within the within the potential, well, they are in principle extend to infinity and do exponentially damped do so, right? So you're able to solve in an infinite domain is what I'm asking.
No, for that we'd need like a bound like minus infinity to plus infinity, and that's not something we've implemented.
No, but what I'm asking is, in the way that you had presented that, okay, here, right? Where do I see the? I mean, in this case, oh, I see that -3 to 3.
Yes,
is where you're
that's
solving
that's where the bound is cut off.
I see,
yeah.
and that boundary condition is what? There.
Then that's a Neumann boundary condition. Neumann zero boundary condition means no flux. Yeah.
But you know, I was thinking in acoustics, you had this trick to approximate an infinite domain with an impedance.
Yes, but
it's a very clever trick.
Yes, so there
is. If there's a quantum mechanics trick like that.
But wait a minute, that's like the impedance of free space or something, or what?
Yeah.
So that doesn't work. You only have two choices. Either you have bound states, then it doesn't matter if you have a big enough domain, or you have a scattering problem, and the scattering problem you can't easily, without a lot of machinery, solve otherwise.
Right. So I mean, what we're dealing with is bound state problems here. Scattering problems is a different. We need a different. We're not interested in the eigen.
Yes and no. Oliver has a couple of nice examples, but you make the domain still big enough that the boundary doesn't matter.
So like a wave packet scattering off something.
Yeah. Further down, you'll see that.
Yeah.
But I mean, if we actually want the S matrix or something,
then we are out of luck if we want the S matrix. Or the T.
Or R, if we really want to go for other letters, matrices with other letters. I think the R matrix is what people talk about in chemistry a lot.
Yeah.
We have another design review coming up right now, but I want to see more quantum mechanics here. Help. What's happening here? Okay, what is this? Is this Schrödinger equation in a torus?
Yes.
That's classic, and it doesn't have zeta function as its eigenvalues.
No, Buminovich cannot be solved in closed form.
What's that?
Buminovich stadium cannot be solved in closed form.
Whose stadium is this?
Buminovich.
Oh, I've vaguely heard that.
It's the kind of the classic one for this many Michael Berry type conjectures about the statistics of high order wave functions. Know the conjectures, know the domain areas, and so on and so on.
Well, hopefully we can reproduce that here, which is cool. What is this now? What is this? Time dependent Schrödinger equation. Why does that have a PDE back? Oh, that's just temporary.
It's still in the context. As soon as it's approved, it's gonna go.
Okay. H equals 0. I don't understand this. That's boundary conditions.
That's a Gaussian wave packet that in a square well flows to the left, right, and then later has a revival.
Okay, but what's the this H? I see. This H here is equal to 0. Right. And this is the initial condition,
yep.
That's the boundary conditions. Okay, I get it. It's cool. What's that creature? Bothers me to see time going up the page like that. What is this? I mean, it looks kind of like nonlinear Schrödinger equation, but it isn't. It's linear Schrödinger
nonlinear time-dependent Schrödinger equation. So it has a potential of phi squared.
What do you mean? I mean, the standard quotes nonlinear Schrödinger equation is not this. It has a nonlinear determinant, doesn't it?
It is nonlinear if you look at the H.
Look at the output.
Yeah.
Conjugate phi times phi squared.
Okay. That's why this looks like the Schrödinger equation. Okay. But that's not a physical thing. That will be something where you have the probability density inside. I'm confused here. Michael, help me out.
It is something of relevance for Bose gas, condensed Bose gases.
Okay. Why? I mean, how do you get, so that's an approximation to the condensate somehow?
Yes, kind of, because we approximate in mean field all the high order many body.
Okay, fair enough. Fair enough. Fine. Okay. That's cool. All right, what's this? I'm now time dependent Schrödinger equation with a harmonic oscillator. So are we about to see scattering against a harmonic oscillator potential? Vertical and horizontal axes.
Not in a harmonic oscillator, on a Gaussian potential.
Yeah, right. So I don't quite understand this. This is a
we move with the package coming from the left, part gets reflected, part gets transmitted, and we get some interference fringes.
That's pretty cool. It's pretty cool. I mean, I think that might look good as a 3D sort of profile. And it also really bothers me to see time going up the page, but so it goes. I mean, if it's easy to flip around, I would flip it around. I think it will be easier to understand.
You can do scaling function reverse for one of the axes, for the Y.
Yeah, if it matters. Okay.
Should we do that?
You could try it.
I don't know. Michael, what do you think?
I would prefer time going up, but I have arguments with various people about this opinion. So
we can, I mean, we can at least show that it's possible.
Yeah, somewhere. Yeah.
Then people can choose whatever they prefer.
This one is cool. You should look at this one. This is the coolest of all.
Press play.
Which one? This thing here?
Yeah.
Oh, that's a. I mean, where were the slits when the wave packet didn't hit them? They should have been in the picture, right?
Unobserved slits are not there. No, I'm joking.
Schrödinger slits.
So this has a potential that corresponds to those. Where is it? Region union, blah, blah, blah. That makes the slits. Okay. Well, this is quite interesting. So this is a Gaussian wave packet that hits them. Is that true? What's the initial condition?
Yes, it's a Gaussian wave packet that is it has a momentum, an initial momentum, and then it hits the slits.
That is pretty cool. So the wavelength is determined by the mass parameter in the Schrödinger equation. Is that true? The thing we're seeing, the wiggles there. What's the
mass
parameter
and
that determines the wiggles?
speed.
Oh, it's the momentum. It's the de Broglie wavelength or something.
Yeah.
Is that right?
Yeah.
I want to see this for longer time. What happens if you go for longer time?
You hit the end of your universe of the box you confined everything in. And then you get a lot of interference from the walls.
I guess I didn't know, although it might be kind of obvious, that you get essentially interference fringes on this side as well. It's kind of obvious, I suspect. I also didn't know that you got that kind of rippling, which is also kind of obvious because you're getting waves reflected back here.
Yeah.
And but then why don't you get sort of de Broglie ripples on the other side? Why are these things here streaming out without having any kind of wave-like behavior there?
Because you just continue like the free wave packet wouldn't do it either. That's kind of part of the free one that goes through.
I see.
And only the other one gets early reflected because of the Derived boundary condition.
Right. So this one is having interference with the reflected
Exactly
stuff.
Yeah.
Huh. Okay, I've never seen this before. That's cool. Is it in quantum mechanics textbooks these days? I don't know.
Yeah.
This is?
Yeah, I think so.
About
this was already in the Schmid book from this mathematical visual quantum mechanics.
Oh yeah, I remember that book. That was a nice book. All right, now I'm that was less exciting.
No, you must wait long enough.
Oh, what's going to happen here? What is this? This is a wave packet that is in some kind of orbit.
Magnetic field, and it's slowly kind of, because the initial one is not quite an eigenfunction, so it slowly disperses.
I think it's pretty cool to be able to do that in the magnetic field. So
sure.
Yeah.
All right, there's a lot of cool stuff here. There's Slater determinants. Wait a minute. This is multi-particle
that's
stuff?
design stuff for the future.
So is there a thought about how to do coupled Schrödinger equations?
Yes and no. So in a way, so the thing is we can generate the equations, but we can't solve them. That's basically the issue.
I see. But which aspect? I mean, with respect to the anti-symmetrization or what?
I'm sorry?
With respect to the symmetrization, anti-symmetrization or what?
Dimension.
Just, I see. We can't solve them because it's too hard for our finite element methods or what?
Because we don't have any solver right now that solves these type of things.
What kinds of solvers have people developed for these?
Beats me. I don't know.
Michael?
I think typically not finite elements, and if finite elements, then reduce to one particle and symmetrize afterwards.
I see.
I mean, this would be, I think, a whole new class of a solver.
Okay. Well, very interesting stuff. All right, I think it's time for our next meeting here. And oh dear. Okay. Great. Anything else I should make sure to look at right now?
I think you've sampled everything.
A lot of nice stuff. Very complicated. Are we going to put out these monographs as like actual books?
Yeah.
It's in the making, yeah.
Okay. I'd like to have them on my shelf. They will be easier to refer to.
Mm-hmm.
Should I sign it?
Sure, you can, yeah.
I trade one. Give me one of yours, I give you one of mine.
Good.
How about that?
How many pages is it?
I don't know. I think all in all, maybe 1,000 or something.
Okay. But Michael is still the all-time winner.
Yes, we can't compete with him, can we?
Okay. All right. Very good, guys. Thanks a lot.
Thanks a lot, Stephen.
Yeah.
Bye now.
Okay. Bye-bye.